car. And then it was totaled.
All right. Good morning to you. Sequences in series geometric. Going to finish this up today. Be due on Monday. Because Raul wants homework this weekend. That's what he was telling me. He says, be real, Mr. Heron. Teach us and give us work to do because that's what a real faithful math teacher does. And I agree. I am here for your good and for your future growth in math knowledge. All right. So let's add these up. All right. So when we're adding them up, the plus signs, remember we have an arithmetic A sub n and S sub n formula, and we have a geometric A sub n and S sub n formula. You with me? The last section, 12.2, was arithmetic, right? Arithmetic, meaning where you arithmetic, add or subtract term to term, right? You with me? You getting the big picture? We did arithmetic back in 12.2. That was where you add or subtract from term to term. We had an A sub n formula, which was A1 plus n minus 1d. We had an S sub n formula, which was n over 2, A1 plus AN. Now we're in the geometric section. For geometric, what is a geometric sequence? Here in 12.3, it means you multiply. So you multiply, I'll just write MUL. You multiply from term to term, and we have different formulas. The A sub n was A1 times r to the n minus 1. The S sub n was A1 times 1 minus r to the n over 1 minus r. I'll give you all four of those, and even one more, which we'll get in a few minutes, on the top of the next exam. Both parts. You won't have to put a 3x5 card at all. So it'll all be up there for you. So you just have to know how to use them. So, all right, so which one's this? Well, it says geometric right here, and they're being added up. So it's S sub n for geometric. It's this one, right? All right, so here we go. To do that one, to use that one, we need to know A1 first off. Do we know A1?
Yeah.
What is it?
1/7.
It's the first term, yeah. It's 1/7. And then we need to know R. Do we know R? How do we find R?
Oh, 6 over 1.
Correct. Yeah, it's what's being multiplied every time from term to term, right? So let's figure that out. I mean, it is that, but in case you're not sure, it is 6, and I would do it that way too. I would just look from here to here and go, look, what was multiplied to make the first term become the second? 6. Not the 7, notice. The 7 has been there all along. The 7's not changing. The 7 is a fixture they all have. It's not what's changing. The R is what makes the jump happen, what changes from term to term, right? What's changing from term to term is it's multiplying by an extra 6 on the top every time. That's the R. So yeah, if you could just look at that and go, look, the R is 6. Great, more power to you. Glad you could do that. If you're not sure, if you've ever got a real ugly one or weird one, and you're not sure, just take second term divided by first term. So the R will be second term over first term, which is 6/7 over 1/7. Remember, that's how you can formally find R anytime you need to. Take the bottom, flip it up. So that'll be 6/7 times 7 over 1. 7's cancel. 6. The R is 6, as we said. Okay, so we got our A1, we got our R. Here we go. S sub n is A1, 1/7 times 1 minus R. What's R? 6 to the n over 1 minus 6. Good so far? I'm going to go to a fresh screen, and we'll keep going. So here one more time. S sub n is A1, 1 minus r to the n over 1 minus r. So it's A1, 1/7, 1 minus r, which we now know is 6 over 1 minus 6. Okay, now we got to work that out. And you can see the answers over there are calculator, decimal things. So we need to actually compute it. One more thing we need n. We got to plug in, then we can just hit the buttons on our calculator. Now, n is the million-dollar question. N typically fools a quarter of the students on the test, a third of the students on the test. This kind of a question with n fools many, many a well-intended student. Doesn't have to. If you study this and get this, spend some time on it, you can all master it. But many that are not here today or won't spend enough time thinking about it will be fooled on the exam. But you're here, so that's good. You're here to hear it. What's n? What does n even mean? Before we get to what the number is, if somebody just said, what's n mean in this form? If you don't know what it means, you have no chance of actually getting the right answer. What is n?
The number of times multiply.
Number of terms, right? N is the number of terms. We clear on that? N is always the number of terms that we're adding up. Like, how many terms are there?
10.
Raul says no. And I always go with Raul's answers. What do you think, Raul?
I don't know why. But I know it's not 10
How do you know?
because you start at a 0, right? So you
Good
include a
job.
0.
Good job. Yeah, it's not 10, it's 11. And that's the mistake people make. You can't just look at this power. Now, I'm not saying it's not that power. Sometimes it is. How do you know? Look at the powers on the sixes like a counter. See this 6 to the 1 there? So from here to here is 10. And this is one more. So there's 11. So watch out for that, right? There's 11 terms. A lot of people put 10. Now, don't misunderstand me. Don't say, oh, okay, so Mr. Aaron says just look at that power, it's always just add 1. No, that's the trick. Sometimes they skip this first one and they just start, then it would be 10. So sometimes it is that number, sometimes it's that number plus 1. It depends if they put an extra term in the front or not. And they change it up. They don't always do it the same. How do you know? Just find out where the 1 is. You know from there to there's 10. Is there 1 extra? There is, so it's 11. Make sense? That'll work for you. So put in your 11 there. All right, now, if you're real good with the calculator, you can just type it in now. I think it would be helpful to take maybe one more step of by hand simplification. 1 minus 6, that's negative 5, right? And then I would just multiply these two denominators together. So get 1 over minus 35. I think that would be easier to type into your calculator like that. So then type that into your calculator. There, basically what I did, I just multiplied the negative 5 times 7, negative 35, and then just calculate it. Now, important that you do that. Go ahead and do it in your calculator, because you'll get something, it's not the way you might think. The answers are a little funny looking. I'm getting the following number. 103656 30.14. So 10,365,000, blah, blah, blah. You guys getting that on your calculators? This will obviously be on the graphic calculator part. I don't think you can do 6 to the 11th by hand. So let's be the graphic calculator part. Now, which of those answers is the right one? They all kind of look pretty different. What's up? Yeah, first off, it's been rounded to 3 places. See this 1036? That will round to 104. So it's not the 607. Those are out. It's one of the 104s, isn't it? Now, what's with that times 10 to some power thing? Yeah, do you know what that means? That's scientific notation. Means move the decimal right that many spots. So let's take the 1.04 times 10 to the 7th. That means decimal right 7. 1, 2, add them to the edge of the number. The other 5 will bring in zeros, won't they?
Yeah, that's good.
7 place right. Is that the right number? Let's put the commas in. That's 10,400,000. Is that what I got here? Yeah, 10 million. That'll 365,000 will round to 10,400,000. That's our answer. It's not the other one. The other one would go 8 places. So you'd take 1.04, you'd go 2 to the right, and then 8 places means 6 more. That would be 6 zeros. That would be 104 million. That's too big. We're talking 10,400,000. It's the first answer. Good? Able to do that in a multiple choice deal? Yeah. Yeah, so I took the 1.04, the decimal was right after the 1, and the 7 means go 7 places to the right. That's what that scientific notation means. So I did 2 places to the right, and I was to the edge of the 104. The other 5 places beyond the edge bring in zeros. So that gave me 5 zeros.
No, how'd you get that number?
Oh, this?
Yeah.
Calculator. Yeah, so I'm glad to help you after. Come on up. All the calculators are a little bit different. Yeah, so I'll be glad to help you. 10 seconds, I'll be able to help you after. Yeah, if you have trouble getting this on your calculator, come on up. Be glad to help. But this on the calculator should lead to that. Anything else on that one? Is that one good? All right. We've done a lot of sigma notation problems at this point. On the sigma notation problems, we always need to crank out like the first 2 terms. Have you noticed that pattern? We got to get the first 2 terms so we can get the R. Right? Second term divided by first term gives you the R. So you got to get the first two terms. So let n be 1 and let n be 2. Find out the first two terms there. So plug in n equals 1, plug in n equals 2, get those first two terms. So 3/7 to the 1, that's just 3/7. And 3/7 squared, that's 9/49. Okay, so now from that, can you get the R? R is always second term over first term. Second term over first term. 9/49 over 3/7. We always grab the denominator and flip it up. So grab that 3/7, flip it up. 9/49 times 7/3. 7 into 49, 7 times 3 into 9, 3 times. It's 3/7. It's the same thing. So the R is 3/7. The first term is the A1. The first term is 3/7. The R is 3/7. We're ready to go now. So now this big Greek S means sum, right? So it's the S sub n formula. So A1. Oh, and how would you recognize, by the way, how would you know it's geometric, not arithmetic?
The power.
N's in the power zone. That's always that's more powerful, huh? It's geometric. 1 minus r to the n over 1 minus r. All right, can you plug stuff in? And they want a decimal, so they want you to crank it out on your calculator. So let me let you type that in. See if you can get that on your calculator. Feel free to check with those around you. Get the calculator things going well for you. What's the n? How many terms up there?
15.
15, right? Because it goes 1 to 15. So that's no tricks on this one. N is clearly 15. Because it goes 1 to 15. Oh, yeah, it does lead. Yeah. And that's the same thing as 10 to 14. Yeah, good. Yeah, on your calculator, it might tell you like an E thing. Anybody else get the E thing? Yeah, and that's the same as scientific. E14 means times 10 to the 14 means decimal to the right, 14 places. E stands for exponent. That's what the calculator is saying. 10 to the 14. 14 is the exponent, it's saying, of a 10. 14 places to the right. Same thing. All right, so A1 is 3/7. A1 is 3/7 because that's the first term. Times 1 minus R. R is also 3/7. To the n, n is 15. Number, goes from 1 to 15, 15 terms. Over 1 minus 3/7. We good to there so far? Okay, now, what should we do with that? Well, I'm going to, have you noticed the pattern in dealing with this kind of big, messy S sub n formula? I always let the denominators multiply. That makes things easier. So I'm going to let that 7 distribute through. I always let the two denominators multiply, right? So that 7 is going to go boom and boom. So what are we going to get? 7 times 1 minus 7 times 3/7. Everybody with me there? Everybody seeing that? And the top is 3 times 1 minus 3/7 to the 15th. Good, and these cancel. Is that okay there? You guys tracking with what I did? I pretty much, you always want to simplify these by letting the denominators multiply. So the bottom is now 7 minus 3. Which is 4. Good? Everybody see what happened when those two denominators multiplied? Right? So that 7 went boom, boom. 7's canceled here. 7 minus 3, 4. So hit the buttons on the calculator now. So when you hit the buttons on your calculator, you should get 1 minus. Make sure that 3/7 is in parentheses. I'm getting 0.749999, so they want me to round to 3 places, so it's just going to be, 750 actually, isn't it? 0.750. Did y'all get that? On the calculator, 0.750. Let me put it right here. 0.750. .750. Questions I can answer on that one?
I just got 0.75.
Just straight, huh?
Huh?
Just 7.5 straight?
0.75 add without the O.
Yeah, yeah, it's the same thing. Yeah, the O is optional. All right. All right. Okay. This question has something. What, will you tell me? Is there any? Notice there's something different about this question compared to the last few we've done.
There's no end.
Where's that?
There's no end. Dot, dot, dot.
So infinity?
Yeah. So we're adding up an infinite number of these things. Do you get the idea? We're not just adding up 10 of them or 100 of them or 1,000,000 of them or 1,000,000,000 of them. We're adding up an infinite number of positive numbers. Think with me on that for a second. I'm adding 1/4, 1/16. The next one, the bottom just keeps being multiplied by 4, right? So it'd be 64, and on you go. So I'm adding up an infinite number of positive numbers. What does that mean? Can you add up? What if I said I'm going to add up positive things forever, which is what they're saying, right? I'm adding up positive numbers. There's no negatives there. So there's no taking away. It's always getting bigger, in other words, right? I'm adding more and more and more and more. They're all positive, aren't they? I'm adding up an infinite number of positive numbers. What happens when you add up positive things forever?
It'll keep going on forever.
What do they all add up to be in the end? Doesn't it have to be infinity? Can you actually add up positive numbers forever?
Well, no, because that's going by, it's increasing by 1/4 every time, but it'll soon get to the point where it can't increase so much, but it'll keep increasing.
So you just said where it can't increase so much, but it'll keep increasing.
Yeah, because it's the increasing value is going down by 1/4 every time. And
Right.
At some point, it'll be to the point where it is increasing, but it'll never reach infinity, because it'll keep shrinking in value.
So it'll always increase, but it won't reach infinity. Is that true? Can you add up positive numbers forever and have it not be infinity?
Prime numbers, right? There's going to be odd numbers as well, so.
What? I don't see. What do you mean?
You said add positive.
I'm just saying these particular. I'm just generalizing. I'm just saying we're adding up these numbers, which are positive numbers, right? None of them are negative. And we're adding them up forever.
So you won't reach infinity then.
You won't?
Because you're only increasing by so much, and the value you keep increasing by keeps shrinking, so you'll never reach it. You'll go from like a rabbit to a snail, and then from that to slower, and you'll never really reach.
Never really reach up. What if I said, hey, I'm going to throw trash in that trash can? I'm going to throw trash in that trash can every 10 seconds, and I'm going to do it
Are you gonna make it in?
all day. Well, I'll stand right by it. I'll throw trash in that trash can all day long. Every 10 seconds, I'll throw more trash.
But you're gonna run out of stuff.
No, my question is, will I overflow the trash can?
Yeah.
It depends on how big it is.
Doesn't it depend on how big it is? What if I say, I'm just going to throw away a little bitty tiny piece?
I mean, it's
Every 10 seconds. Every 10 seconds. All day long. Will I overflow the trash can? Well, no, not if it's small enough piece, huh? Right?
Yeah.
Right? So I'm adding, now, so that's positive pieces of trash. I'm not sure what a negative piece of trash even would be. Positive pieces, actual growing, right? The amount of trash in the trash can will be growing.
Well, then
every
what does
10
the trash
seconds.
can represent? Infinity? Or what does
No.
that represent?
Well, if it overflows, that's my very question. Could I throw trash in that trash can, actual trash in that trash can, every 10 seconds for 24 hours and not overflow the trash can?
Yeah. You can.
Well, yeah, if it's small
Teeny
enough.
weeny.
Could I do that all week long?
No.
No.
Have a robot sit here and every 10 seconds throw away
You would need
a
to eat.
really bitty tiny piece of trash every 10 seconds all week long?
No.
You don't think so? What if it was like 5 atoms of trash?
Oh yeah, I can see that. You can grab that.
So it's possible. Yeah, what if I do it all year long? Robot. It's like small enough. What about all decade long?
No.
But your
What
piece
about
would
a
be.
century, 100 years, a millennium, 1,000 years? How about forever? It will never.
Well, you would never reach forever.
So could a robot throw trash in that trash can forever? and not have it overflow.
Oh yeah,
No.
yeah. Not have it overflow. Yeah.
Not have trash in that trash can forever,
5 atoms at a time.
and not have it overflow.
Yeah.
After forever,
Because like that one, you're gonna get to the point where you're gonna be taking so little into it that you'll never fill it.
is that true? Is Raul right?
You're
I
shrinking.
can throw trash in that trash can forever. Not just for 2 million years, but forever.
Yeah.
Every 10 seconds.
Because it's
However,
gonna be shrinking.
As
Trash
long
go
as
in there
I'm
and never overflow. Never? Forever?
Yeah.
Raul is right. But it sounds crazy.
That's
Right? It's exactly what this is saying. Yes,
Because
you can.
If someone
Here's the plan. I'm going to throw away half. I program the robot and I say, robot, throw away half of what is in your hand every 10 seconds. Half of what is currently in your hand every 10 seconds. I give him one whole piece of paper. After 10 seconds, he looks at his hand, he's got one whole piece of paper, throws away half of it in the trash. 10 seconds later, he looks at what's in his hand, half a piece, throws away half of what's in his hand, a fourth a piece in the trash. 10 seconds later, he looks at what's in his hand, cuts it in half, throws it in the trash. 10 seconds later, half of what's in his hand. 10 seconds later, half of what's in his hand. 10 seconds later, 10 seconds later, 10 seconds later. Is he ever going to throw away even the whole paper?
No.
No, because if he did, he disobeyed the rule. The rule was half of what's in your hand. Not all of what's in your hand, but half. So there's always that. Now, there's real life physical limits to this because we know you can't get smaller forever, right? Physics has shown some of this.
If you do, you.
But the analogy works. I could change if that bugs you. The analogy still holds true because I could change it to moving towards the wall or moving in that way. I can say, can I walk that way forever
Yeah.
and never hit the wall?
Yeah.
No.
Yeah.
Here's my plan: half the direction to the wall every 10 seconds. So 10 seconds take how far I am from the wall, cover half that distance. Okay. 10 seconds later, how far I am from the wall, cover half that distance. 10 seconds later, how far I am from the wall, cover half that distance. Half that distance, half that distance, half that distance. I'll never even reach the wall, right? Because at any moment, I'm only supposed to cover half the distance to the wall. There is no smallest distance, right? I can always move a little bit closer to the wall, but never touching the wall. I'm always moving that way. I could do it forever, and I'll never hit the wall. So it holds true. There's truth there. You can add up positive things forever and have them be a finite sum. That's not what we would have expected, is it? Let me ask you one more question about the infinite, and then we'll answer it, because that's what this is asking. 0.9 bar. Do y'all know what that means? The bar means the nines go forever, huh? So I'm hitting on the forever again here. Okay, 0.9 bar. What number is that close to?
To 1.
Pretty close to 1. Pretty close to 1.
But it'll never touch.
But it'll never touch 1, right? It's pretty close to 1. Yeah, Luis.
That's what calculus tries to deal with, huh?
Exactly.
Go from point 1 to point 2. How close is 1 to 2?
Right. Calculus deals a lot with the infinite. That's exactly it. Yeah, the derivative and the integral, the two fundamental things of calculus, are all based on infinite sums, an infinite process. That's right. So 0.9 forever is pretty close to 1, right? Is it exactly 1? No? We're learning a lot today because the answer is yes. It is exactly 1. I don't mean it's close. I mean there is not any difference at all. 0.9 bar is exactly the same as 1. If you don't believe me, check Google real quick. It's true. Now, why would that be? Why would 0.9 bar, 0.9's forever, be 1?
Could you apply that to like real life so I could do instead?
Well, there's several proofs I could give you, but here's probably the one that is most obvious. If you take 1 divided by 3 on your calculator, what is 1/3? What's the decimal? Probably just know it off the top of your head, huh? 0.3 is forever, right? 1/3 is 0.3 is forever. They go forever, right? You all know that one, right? 1/3. So those are equal. Those aren't just kind of close. Those are exactly equal, right? 1/3 is exactly equal to 0.3 is forever. So if two things are equal, exactly equal, and you do the same thing to both of them, it'll be equal afterwards, right?
Oh yeah.
What am I going to do to both of them?
That
Multiply by 3. What's 3 times 0.3 is forever? Well, 0.9 is forever, right? You with me? Just multiply that 3 all, Okay, what's 3 times 1/3?
1.
I have 1/3 of a pie 3 times. It's true. 1 is exactly 0.9s forever. There is no difference.
So 1 is equal to infinity?
No. That would be a different conclusion. 1 is equal to 0.9s forever. That is true. And you get the pattern, right? If that is true, you can add 1 to both sides of this, and it is true. Then you get 2 is 1.9s forever. It is. 2 is exactly 1. When the 9s go forever, they sneak into the next number. They really do. It's not just me saying they're close and they kind of do. They really do.
So that's,
Do you get the idea?
So that's why an asymptote at one point comes in contact with an axis.
Well, after forever, whatever that
So
means.
that's due forever.
Not in finite time, it doesn't.
Okay.
That's the whole trick. Yeah, calculus is all about those asymptote lines and approaches, and that's what. Yeah. So after forever. I know that sounds funny, but that's exactly the point. We can think about it, we can conceptualize it, we can do things with it, and it's very important. I mean, tons of engineering and things we do in everyday life has used that concept to accomplish much of what we enjoy.
So you could get there, and then that proves that you could, but after forever being done.
After forever. So one point. If the 9s go forever, they really sneak into 2.
Okay.
They really exactly do. Here's one more. I don't want to use too much time, but one more way. If to somebody that was telling you, no way, those are different, I mean, I think the best proof is this one that would convince anybody. 0.9s forever is exactly 1, not just close. But here's another nice proof. If I subtract 2 numbers and the difference between them is 0, what does that mean about those 2 numbers?
They're both equal.
They're equal. They're the same number. If there's no difference, there's no difference. And they're the same number, right? Well, if I take 1.01, and I subtract 0.9 bar, what do I get?
1.
Well, you can't do. The problem with 0.9 bar is the 9s go forever. I mean, how do you even start to subtract? You're supposed to start on the right edge. I mean, what is the right edge? Right. That's a problem. But we could follow the pattern. Well, what if I just had 1 9? 1.0 minus just a 0.9. I'd get 0.1. That would be the difference. But there's not just 1 9. The 9s go forever. Okay. How about if there were 2 9s? Well, then you would get 0.1, right? If the 9s stopped after 2 9s. But they don't stop after 2 9s. They go forever. Okay. What if there were 3 9s? Well, then you would get 0.01 if there were 3 9s. But there's not 3 9s. The 9s go forever. Okay. What if there was 4 9s? Well, then you would get 0.001 if the 9 stopped after 4 9s. But they don't stop after the 9. They go. You get the idea. So really, they go forever. So really, truly, if you did this subtraction, it would be O's forever, and then eventually,
There's a 1.
after
Whatever.
Infinity.
forever, the 1 would come.
Because it's like a circus, like one of those merry-go-rounds. You'll loop, and then you'll come right back.
After forever, the 1 will come. What if I said, hey, I'm feeling generous, going to give you A's for everybody. A's for everybody. I don't like to play with grades. $100. $100 for everybody. And I'll give it to you after forever. What have I said?
No.
Never.
Never.
So when does that 1 come? After forever?
Never.
Never. And if the 1 never comes, what's the difference between those 2 numbers?
Nothing.
Nothing. So those 2 numbers are.
That's a good way to
The
tell
same.
someone, like to reject someone, you know?
They are the same. All right. So that's enough with the infinite. Let's go back. So this is an infinite sum of positive numbers, which can have a finite total. Surprisingly, a finite total. So how do we do it? Well, you got a little handy-dandy formula. S sub infinity is a1 over 1. This is the fifth and the last. So we have an a sub n and an s sub n for arithmetic, an a sub n and s sub n for geometric, and now this s sub infinity. See the infinities? That's the forever formula. So I'll give you this one also, all 5 of these in the top of part 1 and part 2 in the next exam. And don't even have to put them on your 3x5 card. But there's a caveat to this formula. He isn't always true. He's only true, he's only usable when r is a fraction between -1 and +1. The only time you can really use him is when r is a fraction between -1 and +1. Like that. All right. So let's crank him out. So here we go. We got to find r. We always need r. So what's r? How do we find r in this one? Yeah. Everybody just see it? Yeah. R is always second term over first term, like usual. 1/4 over 1, right? And anything over 1 is just itself. So it's just 1/4, right? The r is just 1/4. Hey, is that r, is that between -1 and +1? Yeah, 1/4 is between -1 and positive. It's a fraction. So yeah, this is just the way of checking it's a fraction. Yeah, r is a fraction. So that means, okay, use it. Green light. You can use the formula. Otherwise, if r is not between -1 and +1, you say the series diverges. That's why they have this option, which means it does not add up to a finite sum. It takes off to infinity. It's like me throwing a whole piece of paper in the trash every 10 seconds. Yeah, that's just going to overflow. If you do that forever, it's going to obviously overflow. Diverges. Overflows. So, yeah, if the r is not between -1 and +1, then we say the series diverges. So the r is good. He's 1/4. So I can use the formula. Here we go. S sub infinity is a1 over 1 minus r. a1 is 1 over 1 minus r. What's r? 1/4. So then the answer is 1. And what's 1 take away a fourth? What's a whole pi? Take away 3. Oh, it's 3/4 of a pi, right? A whole pi take away 1/4 of a pi is 3/4 of a pi. And then what do you do with the fraction on the bottom? Flip it up. It's 4/3. Here's our answer. Those numbers forever add up to be a finite total. 4/3.
So it's conversion.
So after infinity.
After forever. Yeah, they'll never add up to 4/3 even after a billion terms. They'll be super close to 4/3. But after forever,
Never.
they'll be right on 4/3. We can conceptualize it even if we can't experience it. They add up to 4/3.
So that's how we calculate stuff like the trajectory of things. When
Yeah, it's got a lot of applications. Some things like that, yeah.
Figure that out. If not-
The formula? You mean the a1 over 1 minus r?
Oh,
Oh, you mean like how do they know if it actually goes forever?
And add up all the numbers.
Yeah, they derive the formula. I'd be glad to do that with the office hours. Come on by. It has to do with how they came up with that formula.
Oh, okay.
Yeah, the infinite. It's kind of like the infinite stuff drops out. Yeah, so it's a long story short. I can show you in office hours. Come on by to infinity and beyond, like Buzz Lightyear.
Buzz Lightyear or Buzz Lightyear? You said
Ne-
Buzz Lightyear.
Right, that's the character. Right?
Lightyear.
Okay. All right. So there's our infinite list of numbers there. So notice this one's changing sign. So dot dot dot. So as soon as you see the dot dot dot, you know you're going to use the s sub infinity, a1 over 1 minus r. So find your r and plug in. Be careful. R will be negative on this one. So when you plug into the formula, you got the double negative thing, right? Got the subtraction in the formula. Some people get messed up by that double negative thing on this one. So the r is always the second term over the first term. Second term is minus a half. First term is 2. We good there? And this is 2 over 1. Flip it up. Minus a half times 2 over 1. These cancel. Minus 1? No, what am I doing?
I don't know.
Oh, you're supposed to multiply.
It's 1/2.
Yeah, it's 1/2. What am I doing there? I knew something bad had happened. Now I see what happened. It's minus a half times 1 over 2. When I flipped it up, I didn't flip it. So minus 1/4. There we go. So the r is minus 1/4. Does that fit the zone we need it to be in?
Yeah.
Yeah, it's a fraction. So this just says it's got to be positive or negative fraction. Not bigger than 1, not smaller than -1. It's got to be between -1 and +1. It is. So that's okay. You can use the formula. If that's not, then we just say diverges, we're done. Which means it totals more than infinity. So whatever more than infinity is. It goes to infinity. So anyway, so now figure the answer. Okay, so the s sub infinity is a1. What's a1? 2. Over 1 minus r. What's r? Negative 1/4. See the double negative thing there? So watch out a lot. I know it seems maybe small or silly, but I've just over the years seen lots of people mess that up. So the minus sign in the formula, the minus sign on the r, double negative, positive. So it's going to be 1 plus a fourth. And so what is 1? How do you add 1 and a fourth? Yeah, because the 1 is 4/4, isn't it? So this is 2 over 5/4. That good? And so then you grab that fraction, flip it up, 2 times 4/5. And what do we do with the 2 times 4/5? 2 over 1, 8/5. So there it is. They add up to be 8/5 after forever. Good on that? Questions? Okay, so sigma notation, what do we always do with sigma notation? First two terms. Find those first two terms. Right? K equals 1, K equals 2. Get the first two, because then you get the R, right? If you have the first two terms, you know that what's causing the jump from term to term. So K equals 1. Plug in 1, we'll get 4 times 1/3 to the 1 minus 1. 4 times 1/3 to the, anything to 0 power is 1. 4 times 1, 4. Good for the first term. And then the second term, K equals 2, 4 times 1/3 to the 2 minus 1. 4 times 1/3 to the 1, which is 4/3. Is that okay? Because it's just 4 over 1.
Dividing by 3.
Good. So they got the first term, got the second term. So now we can get the R. How do we get the R? It's always second term, always first. So see how we always do the sigma notation, right? We always just plug in K equals 1, K equals 2, or N equals 1, equals 2, whatever it is. Get the first term, second term. R is the second term over the first term. So that would be 4/3 over 4. 4/3 over 4. And this is 4 over 1. Flip it up. But do it right. Don't do it like I did last time. 1/4. Cancel 1/3. So the R is 1/3. So we got the R. All right, now we're prepared to answer the... Oh, is the R in the zone? Is the R between -1 and +1? Yeah, it's a fraction. So yes, it's okay. Green light, we can use the formula. Okay, so what's the formula tell us? It says that S sub infinity is A1 over 1 minus R. The infinite sum is A1, which is here, is A1, 4. Over 1 minus R, what's R? 1/3. So it's 4 over 1 minus 1/3. So what's that? 4 over 2/3. Kind of run out of room here. Right? A whole pi, take away 1/3 of a pi, leaves 2/3. We good? So then we got to simplify that. So we have, so S sub infinity is 4 over 2/3. Grab it, flip it up. So it's 4 times 3 halves, put 4 over 1. We good? Which is 12 halves, better known as 6. The infinite sum of those numbers, after forever, they will add up to be exactly 6. In finite time, they'll be close to 6. But after forever, they will be exactly 6. That's what that's saying. Questions on that one? Yeah, multi-part, right. We're not going to do all the multi-parts. We've done the other things. But we just got to do the new part. So basically, they're going to give you a formula. And they're going to ask you, oh, it's off the screen here. Arithmetic, geometric, or neither. From a formula. How do you do that? Well, let me give you the facts. Basically, arithmetic, as you know, means you add or subtract the same number term to term, right? Term to term. And the formula has n to the first power. That's the facts for arithmetic. For geometric, you multiply or divide the same number term to term. We're kind of putting the two sections together here at the end. And the formula for geometric has n in power. in the power zone. So the formulas for geometric have n in the power zone. Formulas for arithmetic just have n on the base with first power. Okay, so as we look at this formula, n plus 3, that's n to the first power, arithmetic. Good there? Arithmetic for sure. You don't have to write down my little formula stuff. You could figure it out for yourself, right? You could just say, look, I don't remember Mr. Heron's formula stuff, but I'm just going to figure it out by hand. I'm just going to put in 1, put in 2, put in 3. Just find the first 3 terms. That'll give you 2 jumps, and you'll see if it's a consistent jump or not. Put in 1, 1 plus 3 is 4. Put in 2, 2 plus 3 is 5. That's a funny looking 5. And put in 3, 3 plus 3 is 6. So 4 to 5 and 5 to 6, what's happening from term to term? It's adding 1. It's adding the same number every time, so of course it's arithmetic. So you can figure that out by hand, or you can use my little formula method. Either way. Yeah, then the other part is they say if it is arithmetic, find the sum of the first 50 terms. So that would be the S sub n formula, da-da-da. We did that before, right? I want to show you the new stuff. Okay, so the formula is 4n squared. What do you think? Arithmetic, geometric, neither?
Geometric.
Neither. Right? What were the rules? Let's go back. Arithmetic was first power. Geometric was not second power, but n in the power zone. N has like Hitler, Stalin climbed into power. Bad news, right? So this is neither. Because this is not first power, and it's not in power. N's in the base zone still, but there's a difference. Neither. And again, you don't have to use my little method. You can figure it out. If you just go n equals 1, I'll show you there's no consistent jump amount. You'd get 4. Do n equals 2. You'd get, whatever, 4 times 4 is 16. Do n equals 3. So you can just always just do it this way. 4 times 36. What's happening from term to term? Nothing consistent. You might think at first, well, it's adding 12. But that doesn't work here. Adding 12 doesn't get you 36. You might think, well, it's multiplying by 4. That won't work either. Times 4 works for the first one, but times 4 does not get you 36. It's neither. So either way, that's a neither. That good? Okay, so 29. 2 minus 3/8 to the n. What do you think? Arithmetic, geometric, or neither?
Arithmetic.
Yep, n to the first power. Arithmetic. And then they want you to find the sum of the first. You know what I mean by that, right? You'd use the S sub n arithmetic formula, which is n over 2, a1 plus an, and we did a bunch of those the other day. We need to do that. Find that out. N's 50 terms. A1 is, I don't know, you figure that out. I'm going to move on. Okay, so they're giving me 6, 8, 11, 15, So what's happening? Instead of a formula, they're just giving me some numbers. What's happening from term to term? Add 2, add 3, add 4.
Neither, right?
So it's neither. It's supposed to be adding the exact same number every time, or multiplying the exact same number every time. It's not. It's changing the number, so it's neither. Okay, so 9/10 to the n.
Geometric.
Geometric. N's in power. When n climbs into the power zone, geometric. Then you got to find the sum of the first 50 terms. Then you'd use the S sub n formula for geometric, which is one we were just working with. 1 minus r to the n over 1 minus r, and blah, 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 right? I don't remember saying that.
You said it was too hard. It's not going to be on the test.
It's not going to be on the test. That's true. Yeah, so how do you take a $20,000 salary and increase it by 5%?
R, 1 plus R, 1 plus...
Probably, don't give me anything fancy. None of these fancy forms. Just, what would you do? You got a calculator in your hand, your life depends on it, you got to raise $20,000 by 5%. What would you do?
0.05 to the power.
Yeah, you would just go times 0.05, get whatever that answer is, and then add back the 20,000, right? Know what you would do? You wouldn't need some fancy formula. You could all do that. Well, let's think about that for a second. Let me show you just a shortcut way to do that. You're right. That's what you do. You go times 0.05, and then after you got whatever that answer is, you'd add back the original 20,000, right? You with me?
Yep.
Well, if you think about it, you know a quick way to do it all at once on a calculator. Same thing like if you said you were going to buy something in the store and it's price is, new set of tires, $300, and you're thinking, okay, I got what is it, 7% tax. How much is that going to be with tax? You can multiply by the 7% and then add back the original, but it's quicker to just take the amount and instead of multiplying by 5% and then adding back the original, you can multiply in one step by not just 0.05, because that'll just give you the tax or the whatever, 1. Throw 1 in front of that. Because what's 1 times 20,000? The original 20,000. That'll add back the 20,000 all at once. So just multiply by 1.05. That'll give you the increase, everything, one step. It's quicker. So whenever you want to calculate something, just multiply by 1 point the whatever, and it gives you the increase and the, because the 1 gives you the original, right? 1 times 20,000 is the original 20,000. So if you want your salary to go up every year 5%, by the 5th year, you would multiply by 1.05 5 times. Right? Every time you multiply by 1.05, it goes up 5%, up 5%, up 5%. So the quick way in your calculator, 1.05 to the 5th. Like that. All right, it looks like we're out of time.